now that we've defined what ions are, how we come up with charges for them, and all those ideas, how to name them, we want to return to the idea of ionic compounds. And so we said that ionic compounds are based around ionic bonds, right? And so that is what holds it together. But what does that really mean? Well, we know that ions are always going to form in pairs. If we think about it, a cation has to lose electrons for an atom to form a cation, and an anion, in order to form an anion, you have to gain an electron. So what functionally happens is you have an atom, say sodium, that tends to form cations, that wants to lose an electron, and it pairs up with an atom like, say, chlorine, that tends to form anions, tends to gain electrons, and what happens is an electron is transferred. This idea of a transfer of electron means that one of the atoms becomes a cation and one of the atoms becomes an anion. And so whenever ions form, it's always going to be in some sort of pair with another or more atoms. You never have isolated ions. And so the ionic bonding, what holds the atoms together in ionic bonding, is the attraction of the opposite charges of the ions. The cation is now positively charged and the anion is negatively charged. Opposite and negative are attracted to each other. And so that's what holds the ions together. So the electron is fully transferred. We can see the electron here is now with the chlorine atom for making it an anion. So the electron is fully transferred. You lead to the creation of ions, and the charge of those ions holds them close together. So even though these electrons are changing in between individual atoms, we're getting that transfer from, say, one atom to become a cation, one atom to become an anion. When ionic compounds actually form, it's not just single atoms doing it or single atoms coming together. When we form these ionic compounds, instead, we're having huge numbers of atoms come together, not molecules like we previously talked about. Well, see, that's what covalent compounds do. But in ionic compounds, we have, say, thousands or billions or trillions of ions coming together, and they arrange in a repeating structure that's called a crystal lattice. And so this crystal lattice is a repeating three-dimensional pattern of ions arranged together. And they're arranged in such a way such that the positively charged cations are maximally surrounded by the negatively charged anions. This is actually why they don't form individual molecules, because basically you want as much positive touching as many negative ions as possible. And so, for example, in something like table salt, you have, say, these large ones are your anions and the small white ones are your cations. And so they're arranged in a pattern such that each type of ion is surrounded by 6 ions of the opposite charge. So that's a lot of nice opposing charges that are going to be attracted to each other. And so these are just small chunks of the crystal, say 3 atoms across or 5 atoms across, but this repeats in all directions. So this just keeps going in all different directions in three-dimensional space. And you can imagine eventually you get, say, lots of atoms, and it would still look like a crystal. So the shape of crystals that we see at, say, the macroscopic level, or this is through a microscope, are still representative of the patterns that the atoms are taking at that atomic level. And so these shapes of crystals that we can see reflect the patterns of atoms. So for example, like quartz has a hexagonal crystal because the atoms are forming a hexagonal pattern. They form rings like that. So since we don't really want to be, even though that's how ionic compounds exist, we don't really want to be talking about thousands of atoms at a time in, say, a formula. So instead, for ionic compounds, we use what's called the formula unit. This is the smallest ratio of ions in an ionic compound. We would use it in just the same way like we use the molecular formulas that we talked about previously. So for example, in table salt, we had this, cubic pattern. You could have thousands, billions of atoms, but you're always going to have one sodium cation for every one chlorine anion. It's always going to be 1 to 1. So if you have a billion of one, it's a billion of the other. So for our formula unit, we just say NaCl. We just say for every 1 sodium, there is 1 chlorine. And that's going to be a manageable ratio, but we do want to always remember that is in fact a ratio, and it's technically called a formula unit. Sometimes, or a lot of times, I'm going to call it the molecular formula. That's common to see, even though technically it's not a molecular formula because there's no molecules for an ionic compound. This also brings us to an important fact. Previously, we said there were rules for how the order of atoms in a formula. And now we have our first one. For ionic compounds, the cation is always first and the anion is always second. So we always put the cation first, anion second. It's similar to the pattern. Cations are always on the left-hand side of the periodic table, anions are always on the right. Same idea as that. So that kind of flow, cations always first, anions always second. All right, so we're looking for questions for participation 6.5, our first Friday participation. This will end module 2, and then we'll have the homework due Saturday covering all of this material from chapter 2 about atoms, compounds, periodic tables, good stuff. Also, to finish up the week, we got to take care of the post lab for the water purification lab. That is due Saturday. If you have any questions about anything, let me know. Making it to the end of the week, much fewer assignments due. Of course, next week they'll all be back, or new versions of them will all be there. If you have any questions about anything, let me know. Otherwise, welcome to this second set of videos for this module, the end of chapter 2, using all the stuff we learned yesterday to apply it to compounds. If you have any questions, let me know. Otherwise, see you in the videos. Bye-bye.